Now we are going to see how we can construct the FA, for which you may not be, you can specify, you can let the machine to make the choice to decide for the input, but you can give the possibility for the given input and from the state, and let the machine to decide to transit from one place to the another place. There may be the, in this case, there may be the situation that your machine may need to make a guess, because for from some state for the same input, it can go to the different places. Consider one example. See, if you are given some regular expression, like, so how you can construct the FA for this regular expression? So this is the FA. This is the FA for the language whose regular expression, we can, the language which can be described with the help of the regular expression 1 1 plus 1 1 0 clean star, then final concatenation with 0. Whenever you go for the deterministic finite automaton, then see, for sometimes it seems difficult to construct the DFA directly, and it is not easier. Like if you are solving some problem, instead of writing the program, you just write the steps first. So you should go to the steps, then those steps you can convert into the programming statement. So here we see that if somebody asks you that, okay, construct the finite automaton for some given language, then for complicated complex language, you may feel difficult to construct the FA. So see, like the steps of the programs, you can also have the situation here. See what regular expression says you have. Regular expression says that you have 1 1 union 1 1 0 and then clean star. This means you can, clean star said that you can repeat either 0 times, you can make a sequence of repetitions either 0 times or more number of times. Every times you are going to repeat means you are going to concate with the, if you form the string by repeating 3 times, means 3 times you have to access either 1 1 or you can go for 1 1 0. Simply either this or this. Then for final 0, you can go to this. With this intuition, if you can construct the FA like this. See, I'm going to construct the different FA. I can take a different, like, see, you are it, assuming that I'm in the state Q0. Now, what I need to do, I can have either 1 1 or 1 1 0. So I can say this is the state Q1, and from Q0, if I get 1 1, if I get 1, then I can go to the Q1, and whenever I get further 1, I can come to the Q0. So you are going to repeat 1 1. This is the kind of loop you have. So 1 1 1 1 you can repeat any number of times, and if you wish, then 1 1, then you can go for 1 1 0. So you can also say, you can have, okay. I have, say you have the Q2 here. This is Q2, and this is the Q3. From Q0 you can have the 1. So this is, you have the 1. Then you can have further 1. This is 1, means 1 1 0, and then you have 0. So see, this is 1 1, and here you are having the 1 1 0. So this is going, you are at the state Q0, and you have 1 1. So you are repeating 1 1 1. 1 1 1 you are going to repeat. And if you wish, then after 1 1 you can go to 1 1 0. Then 1 1 0 you can make repetition, then 1 1. When final this 0, machine say that when final this 0 comes, then you can transit to the final state. Say for this, for 0 you are going for the state say Q4, and this Q4 is now, this is the final state you have. So see, this is one machine we have constructed with the intuition that what actually you are doing, you are going to repeat for the case of 1 1. Then if you wish, you can go for the 1 1 0, then further 1 1, then again 1 1 0, or 1 1, then again 1 1, or 1 1 0, then again 1 1 0, and then for final 0 you are going to shift. So this is the kind of intuition of this language. Now see, this is also the FA. This is the FA. Means this is the finite automaton. But in this finite automaton, you see that you are at the state Q0. If you have the input 1, you are going to the state Q1. From Q0, if you have input 1, you are also going to the state Q2. Now see, this is not the machine we have seen earlier, because in earlier cases, for every input 0, for every input either 0 or 1, you have to go for the different places. So see, from the state Q0, you have the 1, you can go to the Q1. You are saying that, okay, from state Q0, you can also go to the state Q2. So where machine can go? If machine is at the Q0 and it takes the input 1, then whether machine should go to the Q1 or whether machine should go to the Q2. What you have made, this machine you have made with the intuition that you think that machine is powerful enough and machine is having the intelligence power. And if your input is say for example 1 1, then 0, and this 1 1 means you have the 1 1, then final 0. So with the intuition, you think that, okay, just like the human being, machine is intelligent, and it says that 1 1 0, it means machine has to go 1, then again 1, and then final 0. It goes to the Q4. But machine, how machine can make the guess? Machine for 1, if machine goes for 1, Q1, then again 1, it comes to the Q0, and for 0, it goes to the Q4. Then says that, yes, I am in the final state Q4. But machine can make the other guess, like from Q0, machine can go to the Q1. From Q2, machine takes input 1 and it goes to the Q3. And from Q3, machine is given the input 0 and it goes to the Q0. And there is no further input, your machine stops here. Once your machine stops your input exhaust, your machine is halting at the state Q0, and this Q0 is non-accepting state. This means that 110 is not in the language. But you have seen that 110 is also in the language. So this is one possible guess. For this guess, machine is not going to reach the final state, and machine says that, okay, this is not final state. Then machine finds some other possible gap. If for every possible choices, if you are not able to reach the final state, then you can say that, okay, the string is not in the language. So if for one choice, like your machine is going to make the choice from Q0, it goes to the Q2 for 1, from Q2 for the input 1, it goes to the Q3, and from Q3 for input 0, it goes to the state Q0. And this Q0 machine, there is no further input here, input exhaust, and your machine is at the Q0. Then machine says that, okay, for this choice, this particular choice, I am not able to reach the final state. Is there any other possible choice available? So machine says that, yes, there is other possible choice. And machine says that, okay, if I can start from the Q0 and for input 1, I can go to the Q1. This is other option. Then for 1, it comes to the state Q0. And from Q0, if you are having the input 0, machine goes to the Q4. And once your input exhaust, your machine is ending up at the state Q4, and Q4 is the final state, and hence for this choice machine goes to the final state. So you can say that, yes, whenever at least one such choice must be there for reaching to the final state, then machine say that, yes, this is in the language. So this is the case, your machine is going to make the guess. So this is the different machine as compared with earlier one we have constructed like this, which is the deterministic finite automaton, which says that for every input from every state, you have to clearly mention that where your machine should go. Machine should not make any kind of decisions. But here, in this case of machine, you have seen here, machine from some state, machine is required to make the guess. Like if you are at the Q0, your machine requires to make the guess for the case of 1. If it is 1, then machine has two choices, either Q1 and Q2, and it decides where to go. So when this kind of situations comes, when machine is required to make the guess, then this is the case of non-determinism. We can say that, okay, yes, this is the machine is required to make the guess. We have not explicitly mentioned, means you think that you have the choices, machine is intelligent enough, and once some situations comes, machine will make the correct guess, and for that correct guess, it will reach to the final state, if such choice is available. But machine present situation, there is no such machine available, or there is no programming language available we have where you can implement such kind of non-deterministic programs. So this is just like the non-deterministic programs actually, means from some state you can make a function choice, like you can say x is equal to choice, say q1 and q2. So, and you are not writing explicit function for the choice, how this choice can be made. You assume that machine is intelligent enough, and from the two state, for the input 1, say for the two state q1 and q2, machine will make the correct choice, and it will go. If there is some correct choice available, then machine must output the correct one. Say for example, if you have the input 110, for 110 the correct choice is what? Machine has to go from the q0, machine should go to the q1, and the output of this choice function will be q1, because this is the correct guess. If such correct guess is available, then machine must make the correct guess. This we believe, but in practically there is no programming language available for which we can let the machine to decide. So this is the case of non-determinism, and this is the machine, finite state machine, because we have the finite number of state, but this is known as the NDFA. This is the NDFA. NDFA means you have the non-deterministic finite automaton. So this is the non-deterministic finite automaton, NDFA, and earlier we have constructed this machine, we have constructed, this is the DFA. So this D means deterministic finite automaton, and this is the NDFA. Here in this kind of machine, construction of FA is very simple, as you have seen. You have just see the language, and you see that, okay, you need to repeat 11 or 110, and for this final 0, your machine should go to the final state. Using this fact, you have constructed the machine very easily. But in this machine cannot be implemented with your programming language. So here you have also seen that from some state, like you are at the state Q3 here, this is the Q3. And from Q3, you say that if input is 0, you are going to the Q0, but you have not mentioned for the 1. If you are at Q3 and your input can be 1 also, so you have not mentioned the transitions here. So machine thinks that, okay, from the state Q3, I don't want the input 1, I need input 0. And that's why you have, with this intuition, you have constructed the machine. But in for the input it is possible that from Q3 also some input, somebody may give 1, although this is not in the language. So your machine should verify that whether this is in the language or not, and it has to make the all possible choices. And for all possible guess, if your machine is not able to state, then say that 1 1 is not in the language. Like for the 1 1, if you are starting from the Q0, you go to the Q1, then again 1, you come to the Q0. Then for 1, you can come to the Q2 and your input exhaust. This is one choice. Other choice, for from Q0 you can have 1, then go to the Q1. From Q1 you have 1, come to the Q0, again you 1, you can go to the Q1. Your input exhaust and your machine is at the Q1, means this is not a final state. This is other choice. Other next choice is also there, like 1. Whenever you are at Q0, you are getting 1. You are at Q2. From Q2, you are getting 1. You are going to the Q3. From Q3, you are getting 1, but you have not made the transition. So machine is going to crash. So you have machine is going to crash. So when machine is going to crash means machine goes to some dead state, you can say, and means from that state it never go to the final state, because machine immediately decide that here if 1 1, then further 1 means it is not in the language. This is for this choice. So if for all possible choice, whatever choice you can execute for the case of 1 1, input 1 1, you are not able to reach the final state, and hence machine concludes that after executing all possible choices, machine concludes that 111 is not in the language. So in this machine, we have the flexibility. If you don't want further input, say if you are at the state Q4, and we know that this is the final 0, this is the end of the sentence, and at the end of the sentence you have 0, and your machine goes to the final state. This means we don't want any further input, and so you have not made the transition for either 0 or 1. This means if you are at Q4 and you still have some input 0 or 1, then machine is going to crash. It means machine is not going to reach the final state here. So this is the NDFA, means non-deterministic finite state automaton. But this NDFA cannot be directly implemented in your computer. First, what you need to convert this NDFA, non-deterministic finite automaton, to the deterministic finite automaton. Then you can implement. So every NFA, non-deterministic finite automata, can be converted into the, simply you can say NDFA, or just books refer that NFA, non-deterministic finite automata. This is the simplicity. So you just say NFA. So any NFA can be converted to the DFA, and later on we will see the formal way to convert the NFA into the DFA. The only advantage of constructing the NFA is to, if you go for the NFA, then it is much easier to construct NFA as compared with the DFA. And once you have the NFA, then you can convert, we can use the algorithm, and using the algorithm you can convert to the DFA. So there is no issue. If you have the NFA, you can convert to the DFA. Means any NFA can be converted to the DFA. NFA, non-deterministic finite automaton. So you can also define what is NFA. See, just like the FA, we have, this is also a finite state machine, and this also having the 5 tuples. This is 5 information, you have 5 things. Q and sigma, again, Q and sigma are what? Finite sets. Q is the set of states, and sigma, this will take the input symbols. Q0 is what? Q0, again, this is the element of Q, and this is the initial state you have. A is the subset of Q, and this is what? This is the accepting states, or you can say A is the set of final state. Delta is the transition function. You have delta is what? Is transition function. So this is the transition function. This is the transition function. Okay. And this is important actually. So how you can define here? transition function of the NFA can be defined like this. You have the some state, you are in some state, you have some input sigma, and like in case of the finite automaton, you will be in some state and you have some input symbol, and your machine goes to the some state. But here, in case of the NFA, your machine can go to more than one state. So you can write here 2 raised power q. So this is the transition function here. And what you mean by the 2 raised power q? 2 raised power q means, so this is the set of subsets of q. Just means you can also say that power set of q. So this is the power set of q means you can write like this. And you know the notion of the power set. So 2 raised power q means the set of subsets of q. So now see the 2 raised power, if you have some states, say for example q0 and q, if you have the only 2 state, if you have q0 q1, then 2 raised power q means what? 2 raised power q denotes all possible subsets. This is the set of subsets of q, and you have the q, you have the 2 elements. So what you have here, so set of subsets of q. What are the subsets here? You have the q0, this is also one subset. q1 is also, you are having one subset. Now the same set also can be subset. So you can say q0, q1, this is also, and you know that empty set is also a subset, and you can say like this. An empty set is, you can also denote by writing the symbol 5. So see, 2 raised power q, if you have only 2 states, q0 and q1, then you have how many possibilities? This is the empty set, and this is q0, this is the q1 subset, and q0 q1. If your output is this means your machine goes to the 2 place, q0 and q1. If your output is this 2 raised power q, your output of transition function can be this, can be q0, can be this subset, can be this subset. So whenever you have the subset q0 q1, this means from that state, for that input, your machine goes to the 2 places, q0 and q1. If your output is only this subset q1, then your machine for that input goes to only one place, q1. If output is q0, then your machine goes to the one place, which is the state q0. And if you have the empty set, if output is this, it means you have not defined the transition, and it means for that, if some input comes, then for that case your machine goes to the empty state. So like in case of the previous NFA, we have seen that here from Q4, you have seen that from the Q4, we have not made the transition for 0 or 1. If you have the 0 or 1 here, then your machine goes to the empty state. So if you have not made the transition, means it is not going to any subset, it goes to the null state where there is no element of Q. So that's why with this intuition, actually, we don't want to write the explicit transitions when such transitions you don't want. Means we know that from Q4, we don't want any further 0 or 1. So you have not made the transition. But if you want to make, then you can, this is like this. And whatever 0 or 1 you receive, you remain in the null state. So because we don't want such situation, means clearly machine says that, okay, if you have further 0 or 1, it is not in the language, and hence you can go to this state, and whatever input you can receive remains in the same state, you never come back to the final state. From here, Q3, if you have the Q3, then if you have 1 here, then we have not made the transition. This means your machine can go to is going to the empty state, and whatever input you have 0 or 1, it remains in the same place. From Q2 we have not made the transition for 0, and if 0 is there, then your machine goes to the empty state for the input 0, and from that state it remains in the same places. Similarly, from the Q1, if you have 0, then you don't want such input, and hence your machine is going to the empty state. This is so this is the situation. With that flexibility also, because your output is 2 raised power q, and 2 raised power q means power set of q, which contains all the subsets. Power set of q means it contains all the subset of q and null set plus the set itself. So you have the set itself, it has the subsets, and it can also contain the null set. So how many possibilities are there? How many elements are there in the 2 raised power q? If cardinality of q is equal to n, if you have the cardinality of q is n, means you have the n number of states, then you have 2 raised power q will have how many elements? This is the set. This is the set. This set will have the cardinality of this set 2 raised power q. The cardinality of this set will be 2 raised power n, where n is what? N is the number of states. So number of elements in the queue. So if you have number of elements in the queue is n, then 2 raised power q will have 2 raised power n elements. Like here, q is equal to 2, and 2 raised power 2 means 4. You have the 4 elements, this, like this. If you have 3 elements, if cardinality of q is 3, then 2 raised power 3 elements, means you have the 8 elements. So in general, you have the 2 raised power n possibilities. This means if you have 100 states in some machine, then you have 2 raised power 100 such possible outputs you will have. So this is the transition function of the NFA, and this is the difference as compared with the FA, where you say that from some state, for some input, your machine can go to the any of the state, any of the subsets of the queue. So trivial case is what? The cardinality of every subset is 1, like q0, q1. So machine goes to the unique place. But if this can also be the output, so it means machine goes to the 2 place for the same input, and hence machine has to make the guess. So this is the definition of the transition function in case of the NFA. Okay, if you are at some state and you have the input x, you are in the state q and you have the input x, can you determine what is the steps, what are the possible states where machine can halt? So this means what you need to determine, like previous in case of we have decided define the delta star transition. So here delta star takes the, if you are at the state q and from q you are given the input x, where input x is not a element of sigma, it is some string from the sigma star. So your input is, you are giving some input, means some strings, some sentences you are giving, and you are interested to know that if your machine starts from the q and on receiving the input x, where it can reach, what are the possible states where your machine can reach. And in this case, you know that since this is the case of NFA, and your machine can go to number of places. So how would you know that what are the states where your machine can reach on receiving the input x? So you can know with the help of the transition functions delta star. So how we can define the transition function delta star? Let m q sigma q0 a delta be an NFA, then the transition function delta star extended. This is the extended transition function delta star can be defined as follows. How you can define? You can use the recursive definition like this. So you can say for any state q which is in the queue, delta star, you are in the state queue and you have the input string is null. And null is the very trivial case, you know that, where you can go. In case of the DFA, whenever you are at some state and you have the input string null, you go to the same place. But here you are going to the same place. But since output of this transition function is what? 2 raised power q. So you have to write in the form of subset. So you have to write in the form of set. So this is one of the subset of q, where you are good. And this is the trivial case. From any state, if you have the null string, you remain in the same state. Second, you can say for any q from the state set of states q, y is any string from the sigma star, a is an element from the sigma, for any q belongs to q, y is from the sigma star, a is from the sigma, delta star, you are at q and you have the input ya. Y is the string from the sigma star, a is the input symbol. Then ya, once you are concatenating string y with symbol a, then this is the bigger string. So if you are at the state q and you are getting the string ya, you need to decide where your machine can go. So how you can you for deciding this, actually the same logic you can use. You are at the state q. First you need to know that what are the states machine can reach on receiving the input string y. And from those states, if you have the input a, then where your machine goes. This is the key. So you can say this is the union you have to make, and you are going to use the transition function of the NF. You have the transition function of the NFA, which is delta. So if you are at the state P and you have the input A, where P is what? P belongs to delta star. You are at the state Q and you have the input string Y. So see, first you need to determine if you are at the state Q and your input is Y. This is the string, not a symbol. So what are the states you can visit? And you know that transition functions output some subset. So this is what? Some subset of Q. This is some subset of Q. So from every element of this set, you need to know that for the input A, where your machine goes. Because on receiving the input Y, your machine can go to the different places, like it can go to the 3 different places. Now from this state, if you have the input A, so P belongs to this. So this is, so P can be either this, P can be this, or P can be this. So you need to decide that if P is at this state, and if P is this state, then from that state, if you receive A, according to the transition function of your NFA, delta is the transition function of your NFA. Delta star and delta is different, you know that. So delta is the transition function of your NFA. From that state, for the input A, where you can go. So you can go to some subset, then make the union. This says that make the union. If you are taking this, if you are at this state and you are receiving the input A, P can be second element. So you need to know where you can go. This is also some subset. If P is equal to this element, from this set, this state, if you are receiving A, then you need to decide where you can go. And you are making the union, and hence this is the some subsets where you can reach for the input string YA. So this is the way you can define, this is the recursive definition. So here you have the This is the recursive definition for the transition. So whenever you are at the state Q, you have the input string YA. You need to decide first for the input string Y from the state Q where you can go. And output of this is some subsets. And from every element of this subset, you use the transition function of NFA for the input A to decide where it goes, and then finally make the union of all the subset, and this will be the output of your delta star Q YJ. So this is the recursive definition of your extended transition function. So how how you can define the language accepted by the NFA? So if you have some NFA IM, then the language accepted by the NFA we can denote by writing LM. LM is the language accepted by the NFA. So this is what? This is the set of X string which is taken from the sigma star. X language accepted by NFA M is the set of strings X which is taken from the sigma star such that delta star Q0 X. This means you are starting from the initial state. Q0 is the initial state. This is the initial state of your NFA. So from the initial state, you are starting from the initial state and you are given the input X. So from that initial state, if you are given the input X, you are going to some subsets of the Q. You are going to some subsets of the Q. May possibly maybe the empty. So you have some accepting states also in the NFA. So A is the subset of the accepting state, and then make the intersection with the A. And if X is in the language, then this is the subset. This subset must contain at least one element from the A. So if you are making the intersection with A and this is not equal to empty, this is not equal to empty, then you come to know that there are some element in this set which is also in the set A. So this means there is a choice, at least there is, if you have at least one such element in this set which is also in the set A, means it is not equal to empty. So it means there is some element which is also the element of set A, and set A is the accepting state. It means at least you have some choices for which your machine can reach to the accepting state, and therefore X is accepted. So if X is accepted, you can say X is in the language if and only if there is at least one such choice available, for which choice, for executing that choice, your machine can reach to the final state. And this is the way you can say the language accepted by the NFA. So for some choice, your machine may not go to the final state, but for some other choice, it may go to the final state. So we need at least one such choice. If there is no such choice available, then we will say that X is not in the language. This means if delta star Q0 X intersection with A is empty, means no element is common. This means there is no such choice available for which for the input X your machine goes to the final state. So then in that situation you can say that okay, the X is not accepted, but if X is accepted, then this must hold true. There must be some element in this set which is also the member of final state. So at least one such choice is there where your machine can reach to the final state. And this is the way you can say this is the X which is accepted by the machine, or you can say X is the valid strings of the language represented by the accepted by the NFA. This NFA is having the benefit only for construction purpose. We cannot implement. For implementation, you must convert first into the deterministic cases. Fortunately, every NFA can be converted to the DFA.